Okay, so here we go, talking about graphs and graph transformations. This should be review, that's why it's white notes. It is stuff you've seen before, maybe just making sure you're solid. So if I give you this graph of f of x, you can see its shape has two semicircles and a line, and we're going to play around with that a little in a couple different ways. First way is numerically and analytically. Say g is defined as a function that uses f, but has some craziness going on. I would expect you to be able to both use that equation and that graph to complete this table. Let's do one together. So if you were to try to see what happens to g when you put -4 into g of -4 would be, well, let's go slowly. 2 minus f of absolute value. -4 goes in for the x. Plus 1 absolute value, close it. Now simplifying, working inside out. -4 plus 1 is -3, absolute value of which is 3. At that point, I use my graph. F at 3. Well, if this is the graph at f and x is 3, then the y, or f value, is -3. So f at 3 is -3. That would mean that g of -4 is equal to 5. Now you try. What would g be at -1? G at -1.
Kane, can you come to the front office? Case is looking for you. Kane, can you come to the front office? Your brother Case is looking for you.
At 0, that's an x of 0. When x is 0, y is 3. So f of 0 is 3. It feels like there I would get -1. Now try g of 2. G of 2. If I put in 2, I get 3 in the absolute value. That's still 3. 2 minus f at 3. That looks familiar. That's the first one we got. Just a little different source. But 2 minus 3 is 2 minus -3, which is also 5. All right, now it's important that you can do that kind of reading a graph and pulling numbers from a graph like we did here. F at 3, what is it? That's a big AP skill. They often ask you to pull points from a graph or interpret a graph. So make sure you can do that. Second idea, let's go on to transformations of graphs. We could take that f graph and change it a lot of ways, shifting it around, reflecting it, or stretching it. So let's talk about each of those in turn. First of all, transformations. This is crazy because x and y behave differently. X doesn't even make sense to me. It's opposite of what seems logical. Y is what makes sense. So look here. In this case, we're saying, what would the graph of f of x plus 1 be? Well, if I did f of x plus 1, then I'm adding 1 to every x value. And so what would that cause the graph to do? Well, it seems like it would cause it to move right, but in fact, it causes it to move left. It will shift it left. Why the heck would it shift left when you add 1? Well, think about this here. Put in a point.
Students, please return all your Chromebooks to the library immediately. Please return all your Chromebooks to the library immediately. Thank you.
If I were to put in -4 in, thinking maybe I would get a point like that, see what happens, well, that would be f of 3, or -3, excuse me. And f at -3 is actually right here, 0. So when I put in -4, I actually get out 0. Sorry, I paused real quick. So you can see when we put in a -4, we actually get a point that behaves like -3. So how would we get that point then? Well, we'd actually have to put in -5 to start with, so that after adding 1, it would become f at -4, and that's how you're going to get that far left point. Now that would mean then that it seems like every point is one left of the one I would expect. So the next point I might say is that one at the axis, which is normally 0, 3, now it's going to be negative 1, 3. And this point here, that's normally at 3, negative 3, now it's going to be 2, negative 3. You can see that in this case, only the x's changed. Really, the y's kept the same. All right, so what about this, f of x plus 1? Well, it's outside the function, so it's like y plus 1, which means to say, or is to say that y will be changed by 1. But this time it's going to actually calculate the y, then add 1, so this will make sense in that it will shift up. The x's will stay the same. So at the original curve, negative 4, negative 1 is going to get shifted up 1, so it'll be negative 4, 0. This point at the axis, negative 3, 0 will become negative 3, 1.
Mr. Rosinski to the athletic office, please.
3, 0 becomes 4, 0. So those semicircle behaviors shifted up 1. And that 3, negative 3 would actually be 3, negative 2. So everything up. Adding and subtracting then shifts. Adding one inside shifts it left. If you were to subtract one inside, it would be right. As far as outside, adding one shifts it up outside the function. Subtracting one outside the function would shift it down. Let's go to next change, which is stretching or squishing. Now, these also tend to get confused. If you're confused, I suggest you use your sinusoid knowledge as an aid. For example, if you know sine of x has a wave that looks like this, and the normal period is 2 pi, and the normal amplitude is 1, then think about what little changes would do. Like this. If you were to take sine of 2x, that, hopefully you remember, causes the period to change. In fact, it's half as much, so it would be more like pi. So a 2 inside, multiplying inside, causes a horizontal squish, which is most definitely not a math word. I can't remember the math word for it, so we'll go horizontal squish. Likewise, if you divide inside, like sine of x over 2,
Eric Christopherson, please return your Chromebook to the library immediately. Eric Christopherson, please return your Chromebook to the library immediately. Thank you.
that would cause the period to be longer, so it's a horizontal stretch. Let's pause and do those graphs. So if this is the f of x graph, these are both horizontal, so x will change. Y will not change. So this point here, negative 4, negative 1, if I graph f of 2x, then it's going to be a horizontal squish. So the x, instead of being negative 4, will be negative 2. The y will stay the same, negative 1. This point here was going to be negative 3, 0. Divided by 2, though, that's negative 3 over 2. And this guy is 0, 3. When you take half of 0, it's not going to change anything, so it's going to be a horizontal stretch, like if I went whoop, or a squish. At this point, 3, negative 3, the x changes by a factor of a half, or half as much, so it's going to be something like 3 halves negative 3. Not a very good picture. Sorry about that. But you get the idea. Horizontal stretch in the next one will take every x value, and instead of halving it, it'll double it now. So at this point, instead of negative 4, negative 1, it'll now be negative 8, negative 1. Negative 1. This guy that was negative 3, 0, now is going to be negative 6, 0 if I change the x. 0, 3 stays 0, 3. So I've taken those semicircles and stretched them wide. And then the line, instead of ending at x equals 3, it'll end at x equals 6. Same y. All right, so the graph was horizontally stretched in the second one and squished in the first. These next ones are multiplying outside the function, so it'll change y. If you multiply outside the function, like 2 sine of x, sinusoid waves would then change the amplitude. Instead of being up 1, it would be up 2. The horizontal would stay the same. So multiplying outside seems to vertically stretch. Likewise, if you did 1/2 sine of x, that would cause the amplitude to be less, and it would be a vertical squish. Try those graphs then. Think what those will look like. Pause it if you like. I'm going to, if you need more time, moving on. Vertical stretch then. That -4, -1, x would stay the same. X stays the same, y changes. So if we still are at -4, but now instead of -1, it's -2. -3, 0 stays -3, and 0 doubled is still 0. And 0, 3 still stays at 0, but the y changes to 6. It vertically stretches the y values by a factor of 2. So the final value, instead of 3, -3, x will stay the same, but y will change to -6. So you get something like 1, 2, 6, vertically stretching. I know it looks linear on the left, but they're curving. All right.
Sophia, Tessio, to the
And
main
vertical
office,
stretches,
please.
vertical
Sophia,
squishes,
Tessio.
-4, -1/2, 0, 3/2, and 3, -3 is 3, -3/2. Oops, that's a little up here. Okay, vertical squish. All right, so multiplying or dividing by a factor causes stretching or squishing, horizontal or vertical, depending on is it with the x or outside the function. Think of sinusoids. All right, moving on to the last. Okay, negatives cause reflections. Negative on the x changes negative x's to positive x's. If I change negative x's to positive x's and switch, then I'm going to reflect across the y-axis. So I will have the linear behavior on the left, excuse me, and the curves on the right. All right. Negative outside the function, that's like negative y's, so it'll change negative y's to positive y's. If I change a negative y to a positive y, or switch the two behaviors, then I'm going to reflect across the x-axis. All right, so if I reflect across the x-axis, then that line, instead of, actually, let's go with the circle. Instead of being down at -1, it'll now be a +1. And how does it bend? This way. And then the other, instead of being above the axis, it's below. And then the line, instead of going down to 3, -3, it's going to go up to 3, +3. Reflect across the x-axis. Okay, check. Last. Now, there's also some messiness with absolute value. Remember the big idea of absolute value. Absolute value of a positive has no effect. Absolute value of a negative makes it like a positive. Keep that big idea in mind as we go here, all right? So, the one that usually students are better at is the backside. This one here. If it's on the absolute value of f, then that means all y's are made positive. Now, if I use those two big ideas, first of all, what about the y's that were positive already? Well, these y's were positive already. The absolute value does absolutely nothing to them. They stay positive. So this part and this part, missed, no effect. The other effect, though, is absolute value takes negatives and make them like positive. Well, this little circle that was being negative-wise now is going to be flipped up and positive-wise. This little part of the line that was negative-wise is going to be flipped up and made to positive-wise. So you look something like this crazy W-ish thing. The harder one is absolute value on the x, because it has a bit of a gotcha. Okay, so sorry, finishing the second part, absolute value on x. Remember that positives have no effect, or absolute value has no effect on positives. So this place, where the graph had positive x's anyway, there'll be no change. When you put in 3, absolute value of 3 is still 3, you're still going to get negative 3, and so on. Okay, so this part, no change. The change is on the negative side. These, you'll find that, strangely enough, this semicircle curvy behavior never even happens. You never see it because you never actually get to put in a negative 4 to get that negative 1, because the absolute value is going to change everything before you take the function. So think of it like this. Try and put in negative 3. If you put in negative 3, then the absolute value would change it to be positive 3. I shouldn't have done that line. And f of positive 3 is actually over here. It's like negative 3. So this point that I would normally say is right here doesn't even happen. F, when you put a negative 3, it behaves just like the positive version. So this point looks just like this point. And it's going to be a reflection of the negative. Same will go everywhere else. All these negative points will behave just like the positive. So I'm going to get a perfect reflection of the positive side. All those negative sides will look just like the positive side. All right. So next thing, you need to know some basic graphs. Just to remind you, y equals mx plus b is a line with the line intercept of b, and it doesn't necessarily have to have positive slope. That would be implying that m is positive. Y equals x squared is, you know, a parabola, but more generally, y equals x to any even number will also be positive for positive x's, and y would be positive even for negative x's. So think x to the 4th, x to the 6th, x to the 8th. Yeah, they have their differences for sure, but on the outsides, they all go up and up, just maybe a little steeper on x to the 8th and x to the 10th and so on. Also remember that when you take x to the 4th or higher power functions, they can take turns. So x to the 4th could take up to 3 turns, if you remember. It might look like this and take 1 turn, but it could look like this, or it could even look like that, if you remember back to your pre-calculus days. X squared only takes 1 turn, so it feels like the bigger the exponent, the more turns it can take, and in fact the connection is that it's -1. If the power is 2, then the number of turns is 2 minus 1. If the power is 4, then the max number of turns is 3 minus 1, or 4 minus 1, or 3 turns. The bigger the power, the more turns it can do. Let's look at odd. Y equals x to an odd, like x cubed. You know x cubed looks like this, but it could take more turns. In fact, it could take up to 2 turns max and look like that. Generally, x to the odd goes down to the left and up to the right, because negatives in an odd power are negative. That's what you're looking at here, so it's not like an even power. Others, let's go with y equals the square root of x. Hopefully you remember that. X, let's go y squared equals x, the sideways opening parabola. Looks like that. In fact, actually we'll get to that in a second. Let's go logs. Y equals natural log of x. Looks like that. Asymptote at the y-axis. Y equals e to the x is the inverse. It looks like that. It has an asymptote at the x-axis. crosses at 1. And let's review the conics real quick. If you have x squared plus y squared, you're talking circle. X squared minus y squared, or y squared minus x squared, that negative gives you a hyperbola. If you took that circle and stretched it a little, say you divided by a factor, then that will stretch the graph. We know multiplying and dividing stretches a graph, so something like that would be an ellipse. And the last conic section is the parabola. If just one variable is squared, either y equals x squared or x equals y squared, you're talking parabola. All right, those are the conic sections. You'll need that on your homework tonight. All right, this now is an in-class activity. I'm going to give you a page of graphs, and you're going to take those graphs and match them to these equations. So you might say, this equation, look through all the graphs and say, this looks like graph number 2, or something like that. No calculator. Do this without a calculator, just by thinking about what the shapes are, what's the domain, what's the change, what's the shift, what's the reflection, all that good stuff that we just talked about. You're going to use those to do some graph matching. Remember, domain restrictions are what x's are allowed. So think vertical asymptotes, log, square roots. Those are restricted domain functions. All right? I'll give you some time to look that over, and we'll go over it probably tomorrow. That's it for the lesson. Get to work.